What does your housekeeper, your barber, and your mother-in-law all have in common with Henry Eyring and Peter Atkins? They all deal with chemicals and their reactions. Chemicals in your private world on Science Without Walls. Welcome to my home. My wife Barbara and I have lived here for over 25 years. Come inside and visit our front room and kitchen. These parts of the house have been cleaned up, de-entropized for you, our guests. Our front room here is in the very back of the house, so we have a view of the mountains. There's an overhead window facing south, allowing the winter sun to pour in to light and heat the room. Although the more modern parts of the house have double-glazed insulating windows, the older part here doesn't. So to keep the heat in during the winter and the heat out during the summer, we've applied some principles of physics and chemistry. The two living room windows have a blind system to provide about 3 inches of trapped air, which in spite of the oscillations and collisions of those partially trapped air molecules, still functions as good insulation. In the upper south-facing windows, there are 3 specially cut pieces of plexiglass, a transparent plastic. They serve as an inner thermal barrier, trapping about 1 inch of insulating air between the plexiglass sheets and the outer glass. Plexiglass is an organic glass. Its long polymer chains are organized very randomly in the solid material. The chains have no molecular orbitals, which can absorb any of the wavelengths of visible light. So plexiglass is almost as transparent as normal or inorganic glass. So glasses, both silicon-based window glass and plexiglass, are random materials. Their atoms and molecules are not ordered or structured in 3 dimensions, as is the case for metals. Most liquids are also unstructured, with no long-range order. Cooked spaghetti is a good example for the structure of a random polymer. The uncooked, rigid stuff is ordered, crystalline. The strands are rigid, all in a row. But the cooked soft stuff is not ordered. It's random, entangled. If that cooked stuff is frozen, it's still random, but now rigid, brittle, like plexiglass. And because it's brittle and transparent, plexiglass is a glass, a polymer glass. But if we were to heat up plexiglass, it would behave like cooked, warm spaghetti, and could even flow without breaking. So 3 kinds of spaghetti represent 3 kinds of polymers. Enjoy your spaghetti homework. What other polymers or plastics do we have here? Well, they're all over. Barbara arranged to have our hardwood floors finished a couple of years ago. The hardwood contains natural, plant-derived biopolymers. We coated and covered the wood with a highly wear-resistant polyurethane, a synthetic polymer. The name polyurethane refers to a whole class of polymers with a wide range of properties. The foam in this sofa and in these pillows is polyurethane, and so is the elastic part of most of your stockings and underwear. Polyurethanes are easily made with many properties and shapes. A similar chemical reaction is used to make nylons, called polyamides, another very large and diverse group of plastics.
We must have nylons back there.
Dr. Rob Shear is an instructor in the Department of Material Science and Engineering at the University of Utah. Rob does workshops and short courses for people. He calls the workshops Mega Molecules. Here he's doing the nylon rope trick. Watch carefully. Rob has 2 containers, one with water, the other with a hydrocarbon solvent. In the water is a chemical which is water-soluble. In the hydrocarbon, he's put a second chemical. Rob gently layers the light solution onto the heavy one. Watch. White stuff at the boundary. That's nylon. The only place where the 2 reactive chemicals could meet each other and react is at the boundary between the water and the hydrocarbon, at the interface between the 2 liquid phases. The two chemicals react with each other and combine to form a new bond, an amide bond. And the chemicals continue to form long polymer chains, macro or mega molecules. Eventually, the process stops because the reacting chemicals can no longer make contact. So Rob carefully pulls the white stuff away and keeps pulling slowly, exposing fresh interface or boundary and allowing the two reacting chemicals to continue to make contact. And they continue to react. And there you are, nylon rope. We call this an interfacial reaction because that's where it occurs, at the interface or the boundary between the two solutions. Thanks, Rob. The nylon in your nylon stockings and in your nylon-based textiles and clothing is made similarly, except that it undergoes some processing steps to enhance its physical and mechanical properties. You can already see from the chemical structure that nylon has hydrogen bonding characteristics, the NH group and the CO group. They are what makes nylon so incredibly strong. And that's why nylon ropes are often preferred in parachutes and by rock climbers. But enough about nylons and polyurethanes. Welcome back to my kitchen. Here's a Teflon baking pan. Teflon is an absolutely wonderful plastic material with a unique set of properties. It was developed by a former Utah, Bill Gore, the Gore from Gore-Tex. Bill and his wife Vivian received their undergraduate degrees at Westminster College in Salt Lake. And then Bill went on to study chemical engineering at the University of Utah. He went to DuPont and worked on a new plastic, Teflon, polytetrafluoroethylene. Teflon has an incredible set of properties. One is that things just don't stick to it. So it led to the revolution in stickless baking pans and kitchenware. Water beads up on it. Water doesn't want to have anything to do with that Teflon surface. Because the Teflon surface can't bond with water, and so water prefers to bond to itself. Even oils tend not to stick to Teflon. Bill Gore and his son developed a process for producing a very special kind of Teflon, now known as Gore-Tex. Gore-Tex is a material which prevents the absorption and penetration of liquid water, but allows water vapor to penetrate. So you can sweat, and the sweat vaporizes and makes its way through the fabric, so you don't feel wet and clammy. But if you're in the rainwater won't penetrate into the fabric. It works like this. Gore-Tex and other microporous polymers have very tiny holes called pores. The polymer chains are oriented in microfibers, which have little spaces between them. And because those individual polymer fibers are so hydrophobic, that is, they cause water to bead up, water doesn't want to have anything to do with them, and because the pores are so very small, it takes a very high pressure to push water through those pores. So water just doesn't penetrate. If we put water on cellulose fibers, which hydrogen bond to each other and to water, the water wets, penetrates, spreads. Remember, we even made water flow uphill using this wetting process. It's a behavior called capillarity. And capillarity is why diapers work so well. You certainly wouldn't want diapers made of Gore-Tex, not only because it would be very expensive, but because the water would just bead up in a pool and wouldn't spread and absorb into the fibers. So how did Gore make such a fascinating microporous structure? In his kitchen. Gore and his son were experimenting with ways to produce Teflon for use as electrical insulation. Although Teflon seems to have wonderful properties, it was very difficult to fabricate. They heated it, softening it, and then pulled on it. And one time they took a tube of Teflon out of that oven, and since nothing was working, they apparently got annoyed and just pulled on it like crazy. And with that very rapid application of force, it flowed, producing the unique microporosity. That's what we might call a serendipitous discovery. By experimenting and playing with a very wide range of conditions, they came across a condition, a process, that led to a completely new and special set of properties. In this case, based on a new and unique microscopic structure, a microstructure. So the next time you're out, buying outdoor clothing, talk with the salesperson about Bill Gore, Gore-Tex, and microporous and breathable fabrics. And if she doesn't know what you're talking about, teach her. Bill Gore died of a heart attack while backpacking in the Wind River Mountains in 1986. His name is now immortalized in the Gore School of Business at Westminster College in Salt Lake City. There are a lot of other polymers in kitchens. There's the paint on the walls. There are all the plastic containers, which hold our foods, leftovers, and milk. Even electrical appliances have a lot of plastic parts. So kitchens are chemical laboratories. Kitchens have distillation systems. In a coffee maker, for example, water is distilled and recondensed back through a filter holding the ground coffee. And then that hot, steam-like water extracts the caffeine, the color, and the flavors that make up a dark, aqueous solution we call coffee. And it's similar with tea. The solid plant-derived tea material is usually in a bag or holder. We pour hot water over it. The water-soluble components of the tea make their way from the now hot, wet solid into the water liquid passing through it, producing a solution of tea. Probably the most interesting activity in a kitchen, from a chemistry point of view, is cooking, a temperature-dependent process for changing the structure, the properties of the proteins and other fibers in raw foods. A major part of cooking is cleanup, usually the least popular and least interesting part. There are soaps and detergents used to wash your dishes, your clothes, and your floors. Soap is one of our oldest chemicals, probably at least 5,000 years old. Humans have been bathing and washing their textiles with soaps for a very long time. Soap refers to a sodium or potassium salt of a hydrocarbon acid. Remember methane, ethane, propane? Well, if we kept adding carbons, we would make long hydrocarbon chains like octane, decane, and even the very long chains of polyethylene. And remember acids like HCl? Well, there are also organic acids like citric and lactic. Organic acids contain a COOH group from which hydrogen ion can dissociate, hence an acid. Now imagine one of those acid groups on the end of a long hydrocarbon chain. Since fats involve long hydrocarbon chains, we call this a fatty acid. Acid groups in aqueous solutions like to give up their hydrogen ions, becoming negatively charged. So now assume we have a sodium chloride ionic solution. And there's an equilibrium between the COO minus group, the proton, and the sodium ion. We can have a COO minus sodium plus interaction. We call that the sodium salt of that organic or fatty acid. And that's what soaps are. They have long hydrocarbon chains which are the oil-soluble, the water-fearing or water-phobic part of the molecule. And we call it hydrophobic, implying that it shuns water. But it's really the water that shuns it. Remember, water likes to stick to itself. There's no easy way for the hydrocarbon part of that molecule to bind with the water molecules. But at the other end, at the COO minus group and the sodium ion, just the opposite happens. That group loves to surround itself with water molecules and would like to be totally within water, fully solubilized. It can't, because to do that it would have to drag that oil-like portion of the molecule in with it. And it can't, because that part is insoluble. So soaps locate and operate at interfaces between oil and water. Grease and dirt on your clothes and on your dishes are oil-like materials. The hydrophobic tails of these soaps like to solubilize, penetrate the grease and dirt. But the polar heads like to interact with the water phase. Let's stir up the water-soap mixture and sort of force the soap into the water phase. The apolar tails can't really be in water, so the water ostracizes. It excludes, it segregates the soap molecules into tiny structures called micelles. Micelles are little microphases that now float around, actually solubilized in water. And this neat little structure, oil-like inside and polar or water-like outside, is stable and soluble. So the oil or grease on your dishes is actually sequestered in this little capsule. The little capsule, the micelle, is soluble and is washed away down the drain, taking with it the dirt, the oil, and the grease. Acids and sodium salts are not the only polar groups used in soaps. Sulfonate groups are often used. They are extremely polar. And sometimes positive, that's cationic, charged groups are used. And then there are also neutral or non-ionic soaps, which depend on hydrogen bonding for their polarity. Enough about washing and cleaning. Let's get to equipment, to laboratory equipment. We have two systems of producing heat here, electrical heating elements on the stove and a microwave oven. And you already know how the microwave works because we talked about the rotations of water molecules a few programs back. Electromagnetic radiation in the microwave range is widely used for communication. But the place where microwaves have had the greatest direct impact on you and me is in the kitchen. It's the only practical way we have to heat things from the inside out. When we talked about heat earlier, we said it flows from hot to cold. Well, there are three basic ways by which heat flows. If atoms or molecules get hot, they move. They have velocity and kinetic energy. They run into their neighbors, passing energy to the neighbor, which interacts with its neighbor, and so on. That's how molecules transfer heat energy, by mutual contact or collisions. If the molecules or the atoms are all tightly organized in a solid structure, or even in a liquid structure, then that contact is very efficient. We call this mutual contact means of transferring heat energy conduction. If heating results in a change of density, and therefore a change in buoyancy, that mixing process is called convection. You also know that electromagnetic waves carry energy. If those waves are intercepted and absorbed, the energy deposited is usually transformed to heat. If the heat comes in or goes out via electromagnetic radiation, we call that radiation. Microwave heating is all three of those combined. We don't normally associate microwaves with thermal energy because each microwave photon has very little energy. But it has enough energy to activate the rotation of a water molecule, which then de-excites by giving off heat. Depending on the construction of your microwave, water molecules in various regions of the oven get excited, generating local regions of heat. Many microwave ovens rotate the contents to average out these hot spots. The minute you have a hot region adjacent to a cold region, then heat flows from hot to cold by conduction and convection. Because the microwave radiation is tuned to the wavelength that's optimum for absorption by water, things which don't have a mechanism for absorbing those microwave photons don't respond. So that's why these plastic microwave compatible dishes, containers, don't tend to heat up. But if they had polar groups, which can absorb in the same wavelength or frequency range as water, then they would heat up. So don't put your nylons or polyurethanes in your microwave. Microwave heating is a bit counterintuitive, sort of anti-common sense. We're used to the container being the hot thing and transferring the heat into the contents inside. But with a microwave, it's just the opposite. The contents get hot because the contents have water, which absorb the microwave energy. The container only gets hot by virtue of conduction of heat from the hot food inside. The rotational excited states of the water molecules are, to some extent, dependent on the kind of bonding, the kind of interaction between the water molecules themselves and between the water molecules and the other chemicals. So different foods respond to microwave radiation differently. No big surprise. Since foods are such complicated mixtures of chemicals, it's not easy to predict how rapidly or uniformly a particular dish will heat up in a microwave oven. But enough about microwaves. There are several other chemistry labs in your home and mine, like the bathroom. It has toothpaste, which contains a variety of surfactants, abrasives, and perfumes to facilitate the cleaning of teeth. There are bath salts, bubble baths, shaving cream, and body lotions. A garage is another chemical lab and chemical storeroom. There are automobile oils. There's gasoline in the fuel tank of the car. There are paints and solvents for woodworking, and solvents to fix the plastic piping in the lawn sprinkling system. The lawn pipe is PVC, polyvinyl chloride, a polymer produced by the polymerization of monochloroethylene, also called vinyl chloride. All the little vinyl chloride monomers react together to form long polyvinyl chloride, or PVC, polymer chains. So you have several chemistry laboratories in your home or apartment, your kitchen, your bathroom, and maybe your garage. Chemistry is a key part of your world, and there are a number of wonderful books that deal with everyday chemistry. The Extraordinary Chemistry of Ordinary Things is a particularly good one. When you use household chemicals, observe them, think about them, read the list of ingredients. Try to figure out, at least conceptually and generally, what they are and why they do what they do. And of course, consider the potential toxicity and hazards in using them, and the environmental issues associated with their use and with their disposal. And use them safely. Keep cleaners sequestered, isolated, away from foods and away from kids and pets. I have to get back to the dishes. We don't have a dishwasher. I'm the elected dishwasher in this household. But I always let Entropy do most of the work for me. By soaking the dishes, generally for a half hour or so, before getting around to washing them, the water molecules and the detergent have time to diffuse and circulate, get in there, creating maximal disorder in this initially pretty ordered system, thereby contributing to cleaning my dishes. Let Entropy work for you. Use that second law of thermodynamics whenever you can. See you next time.
I'm gonna wash that man right out of my hair. I'm gonna wash that man right out of my hair. I'm gonna wash that man right out of my hair and send him on his way. Get the picture? I'm gonna wave that man right out of my arms. I'm gonna wave that man right out of my arms. I'm gonna wave that man right out of my arms and send him on his way. Don't try to patch it up. Tear it up, tear it up. Wash him out, dry him out. Push him out, fly him out. Cancel him and let him go. Yay, sister. I'm gonna wash that man right out of my hair. I'm gonna wash that man right out of my hair. I'm gonna wash that man right out of my hair and send him on his way. I went and washed that man right out of my hair. I went and washed that man right out of my hair. I went and washed that man right out of my hair and sent him on his way. I went and washed that man right out of my hair. I went and washed that man right out of my hair. I went and washed that man right